Hello everyone, my name is Pengyuan Wang and from Nanyang University. Today I'm pleased to present the work InCLET large language model in context learning can improve embodied instruction following. The domain we focus on is natural language condition reinforcement learning. And the pipeline is the human gives the task and the agent receives the task as goal to interact with real world. In previous work, there always need to train an extra translate to translate the task to Go. However, this will highly rely on the pre-collected data and need an extra training procedure. Furthermore, when the human gives the task, there may exist noise. So we want to find a method which don't need an extra translator and can translate the task to representation effectively. Inspired by in-context vector, we found that the demonstration from in-context learning and can give the good representation. So we want to use the in-context learning to efficiently generate task representations. The first question is, how can we get the in-context demonstration? We use the internal knowledge from LLM to generate the imaginary trajectories, which is the step A. And the step B is which is extracting task representations in context learning. Finally, we can use the task representation to train policy. In the first step, we use the LLM knowledge with this prompt. We need the LLM to generate the imaginary scenery and create the initial state and the terminal state. Then we use this initial state to terminal state, giving the mapping and generate the in-context demonstrations. And then we will use the hidden state corresponding to the error position from the final layer as the representation. Of course, we can use the all hidden state vectors as the task representation. We average it. And it's okay to use this task representation as a condition to train policy. However, if we do this, it's hard for policy learning because the task representation and the dimension is very high and it will give a large burden for policy learning. So we use the technique of random projection to transfer the task representation from high dimension to low dimension. The next section is experiments, where we use the two environments, Frank Kitchen and Clever Robot. In Frank Kitchen, there are 4 subtasks and 8 subtasks in Clever Robot. The description is generated by ChatGPT. And the following figure is our main results. Compared with the baseline board LAM3 and 1 hot, our method can give the best performance from training to testing and in Frank Kitchen and ball. Finally, we want to verify the effectiveness of InCLET. We give the embedding visualization. We can observe that the task embedding generated by InCLET can get closer compared with BORT and LAM3. Of course, we also give the example of imaginary in-context demonstration in the right. And then this is the evaluation study to verify the different modules' performance. We verify the in-context learning module and the random projection. We found that if we don't use random projection, the performance is a little low, but the variance is very high. And if we don't use the in-context learning, the performance is very low. And then we compare with the different fusion methods average or only use the last hidden state, which is shown in the below figure. We found that it's better to use the average performance to give a better representation. And the next we compare with the different modules. Different LLM we found with Llama 3, Gemini, and Mistral, all methods can work well. That's all. Thank you for your listening. And if you want to follow in the code, it's shown in the following link.